Seattle. It's November 13th, 2025. And now for the day's news. For today's security story, Microsoft's November Patch Tuesday includes fixes for 63 vulnerabilities with one zero-day, CVE 2025-62215, which is already exploited in the wild. The zero-day, a Windows Kernel elevation of privilege issue that attackers could use to gain system-level access. Microsoft also rated 4 critical vulnerabilities this month, including 2 remote code execution bugs. The release coincides with the first Windows 10 extended security update. Admins who still manage Windows 10 devices should either upgrade to Windows 11 or enroll those systems into the Extended Security Updates program. As always, prioritize testing and deployment for Internet-exposed services and workstations with privilege escalation path vulnerabilities. For more information, see the links in the show notes. Today's programming language story is an update. It's Rust 1.91.1. It is a maintenance release, a patch release. Some people call it point releases, but it fixes 2 regressions introduced in 1.91.0. The first is a WebAssembly import problem. Projects that import the same symbol name from 2 different WASM modules could hit a import module mismatch linker error. There was another minor issue with locking the target directory when using cargo, and that was on illumos. So this restores the correct build isolation. Minor release, but if you're using Rust, you should run an update. You can do it with a single command. It's rustup -update -stable. So for more information, see the links in the show notes. And for today's Weird Bucket story, Japan is launching the first wooden satellite. Japan launched a tiny wooden satellite, literally made from magnolia wood, to see how timber survives vacuum, radiation, and temperature swings in orbit. The idea is that the wood structures could reduce orbital junk because wood burns up cleanly on reentry, leaving less alumina dust than metal components. It's a 10-centimeter class CubeSat built by Kyoto University and Sumitomo Forestry. The team is testing cracking, outgassing, and structural integrity over time. A wooden spacecraft in orbit is weird, and it might hint at a new thinking about sustainable satellite design. For more information, see the links in the show notes. And for today's other news, OpenAI fights in order to turn over millions of ChatGPT conversations. Reuters on November 12th reported a court demand seeks large-scale conversation logs. OpenAI is contesting scope and privacy implications while regulators and litigants push for broader disclosures. Anthropic has announced a $50 billion investment in U.S. data centers. Also from Reuters, Anthropic will partner with FluidStack on new facilities in Texas and New York to expand AI infrastructure capacity. IBM has unveiled a new quantum chip called Loon, L-O-O-N, and it says it shows a path to useful quantum computers by 2029. Reuters reports that IBM also plans a Nighthawk chip this year and aims to demonstrate quantum advantage on specific tasks next year. That's it for today's news. Let's dive deeper into the IBM Loon quantum chip. What's actually new? So IBM announced Quantum Loon. It's an experimental superconducting quantum processor that demonstrates all the key hardware elements for future fault-tolerant quantum computers. In IBM's roadmap, Loon is a proof-of-concept chip built to validate technologies like multi-layer wiring, long-range tunable couplers, and fast qubit reset that are required for scalable error-corrected quantum computing. IBM says that it has now shown that it can fabricate chips with multiple stacked routing layers and with special crosstalk canceling couplers, or C-couplers. These link distant qubits on the chip and not just its nearest neighbors. Loon also incorporates hardware for rapidly resetting qubits, and this is important for iterative error correction cycles. In tandem, IBM reported a breakthrough in real-time quantum error decoding using classical hardware, FPGAs, to decode quantum error-correcting codes in under 480 nanoseconds. This is a 10x speedup over prior approaches. IBM's Jay Gambetta highlighted that these advances came a year ahead of schedule, and IBM believes that it now has the critical building blocks in hand to achieve practical quantum advantage by 2026. Alongside Loon, IBM unveiled Quantum Nighthawk. This is a new 120-qubit chip designed for near-term use by IBM's client. It's targeted to be delivered by the end of this year. NYTimes features 218 next-generation tunable couplers linking qubits in a square lattice, over 20% more couplers than its predecessor, the 89-qubit Heron chip. The increased connectivity lets NYTimes run quantum circuits about 30% more complex than Heron while maintaining low error rates. IBM expects NYTimes to be the workhorse in demonstrating quantum advantage on certain problems by the end of 2026. Let's talk about gate count and progress there. NYTimes is just the first in a series. IBM plans successive NYTimes generations each year that significantly boost 2-qubit gate capacity. The initial 2025 NYTimes supports circuits with about 5,000 2-qubit gates, and IBM projects by 2028 its NYTimes-based systems with modular coupling of greater than 1,000 qubits could handle up to 15,000 2-qubit gates per algorithm run. This metric of executable gate depth is crucial for tackling more complex algorithms and is being tracked as a proxy for quantum computational power. They also talked about error decoder latency. In a press release, IBM reported that it can now decode quantum error correcting codes, specifically a quantum LDPC code, in less than 480 nanoseconds on classical FPGAs. Now, this is roughly a 10x improvement in speed over previous solutions and fast enough to provide real-time feedback within a single error correction cycle for superconducting qubits, which typically have microsecond scale cycle times. The less than 480 nanoseconds decoding latency was achieved using a relay belief propagation algorithm and met a key milestone a full year earlier than IBM's roadmap had anticipated. Let me take a step back because I just reported a number of facts, but there's so much to explain, and that's one of the problems with quantum computing news, is I just told you about a belief propagation algorithm that's used as a relay. I talked about coupling qubits. We need to really dig into what this means because my assumption is that many people don't fully understand what this is. So let's talk about IBM's quantum processors first, including Loon and NYTimes. They use superconducting transmon qubits, not trapped ions. This has been IBM's chosen platform for years. It benefits from fast gate speeds, tens of nanoseconds, and integration with conventional fabrication techniques. The downside is higher error rates and shorter coherence times, microseconds. And here, IBM is emphasizing that rapid error correction cycle. The other is this interconnect innovation. Loon introduces multiple high-quality, low-loss wiring layers on chip, and this allows signals to route both in-plane and vertically, a necessity for complex qubit layouts. Crucially, IBM has implemented a long-range tunable coupler, a C coupler, that can physically link qubits that are not nearest neighbors. These couplers can be opened or closed dynamically, and this either enables or isolates interactions between distant qubits. So this flexibility is critical for so-called quantum LDPC, and I'll explain what LDPC is later. You require each qubit to interact with a specific set of other qubits, and often not just the ones that it's next to in a grid. The other is the speed with which it can reset a qubit. So the Loon architecture specifically includes hardware to rapidly reset qubits to a known state in between computational steps. And this is especially important for qubits used in error correction. After each cycle of detecting errors, these qubits must be returned to a clean state to be used again immediately. Faster reset means shorter error correction cycles, reducing the window in which errors can accumulate on data qubits. But one of the themes of the Loon announcement is speed. The speed with which things can happen is important, especially in the context of the coherence time. They also have talked about manufacturing. IBM has moved its quantum chip fabrication to 300 millimeter silicon wafers at the Albany Nanotech Complex in New York. And this is significant, but it's also in line with the overall announcement. They're focused on speed. They're publishing a roadmap of the number of gates and how that will increase over time. And this is maybe the most significant part of the Loon announcement. What they're sending here is a message, and that is they're getting ready to start fabricating these chips at scale. The shift to 300 millimeter wafer size has halved development cycle times and enabled a 10x increase in chip complexity. But IBM is trying to send a couple signals here. One is we're focused on the speed of error correction. We're focused on the scale of manufacturing, and we have a roadmap for scaling up useful quantum chips. What they're basically saying is we're not just announcing a chip, we're announcing a chip that we're planning to manufacture at scale. And again, we're still in early times for quantum computing, but it is interesting to take note of IBM emphasizing fabrication. What's disclosed here, IBM and Analysis have shared a qualitative analysis of features of Loon and Nighthawk. We know Loon includes long-range tunable couplers, multi-layer routing, fast qubit reset hardware. Analysts have chimed in. We have direct quotes from IBM's Jay Gambetta and commentary from Mark Horvath, a Gartner analyst, lauding IBM's approach as very clever now that it's being implemented in actual chips. But we have a lot of numbers around the Nighthawk headline specifications: 120 qubits, 218 couplers, 30% higher circuit complexity. What we don't have in this announcement is raw performance metrics for these Loon qubits. Nobody talks about the coherence times, at least as far as I could see. We don't have any logical qubit performance data from Loon yet, the effective logical error rate per cycle, or the demonstrated logical qubit memory time. That data would show whether Loon's error correction is beating the break-even point. And there was no announcement about Loon's availability. I also want to explain some of the acronyms that I've used. LDPC, that's Quantum Low Density Parity Check. It's similar in some ways to what we talked about with Willow, where we have grids of qubits, and we're trying to measure the parity of the qubits to identify errors. So when you have an LDPC error correcting code, it's using many such sparse checks to pinpoint errors without disturbing the quantum data. And that seems to be the trick in a lot of these chips, trying to measure parity without disturbing the state of the qubit. In practice, you have to have extra qubits that periodically entangle with the data qubits to gather these parity bits, and this is called a syndrome. It's actually called an ancilla qubit that's entangled with a data qubit. Now, a fast decoder then uses the syndromes to infer which qubits are likely errored and applies corrections in real time. The promise of quantum LDPC codes is that if hardware can support them, with lots of connectivity and fast decoding, they can protect logical qubits using far fewer physical qubits than older schemes. And that's really the IBM Loon innovation. It has that on-chip connectivity to help realize a quantum low-density parity check. And it has the classical processing speed in FPGAs to decode that check on the fly. And that's also a critical fact to point out. It has an FPGA, a field programmable gate array, and that's a classical computer. That's been around for a while. That's the thing that's decoding the output of this low-density parity check, and it's doing it in a fast enough way to align with the speed of the cycles that they emphasized. All of this depends on a tunable coupler. What is that? Why does it matter? In superconducting qubit chips, qubits typically interact via couplers. And with these couplers, you can let two qubits interact, or you can isolate them from each other. IBM has used tunable couplers in previous chips, like Osprey and Heron, for nearest neighbor coupling. What's new in Loon is that long-range aspect. Loon's couplers can connect qubits that are physically far apart on the chip. This ability to entangle non-neighbor qubits is critical for the low-density parity check codes. And it requires a specific network of qubit interactions that doesn't neatly map into a 2D grid. So this is why the multi-layer routing in Loon is important. By implementing long-range tunable couplers and multiple wiring layers, IBM can create the needed web of connections. In simple terms, tunable couplers let IBM dynamically reconfigure which qubits interact during the computation. And this gives them flexibility. It reduces errors when qubits are not supposed to be interacting. Last, let's talk about these fast qubit resets. They were emphasizing the amount of time that they had achieved. It was less than 480 nanoseconds. In an error-corrected quantum computer, time is of the essence. Each error correction cycle might take a few microseconds. These extra qubits that are used in each cycle to probe the data for errors, after measurement, those qubits are typically left in an uncertain state, and they then need to be restored to a known state. So think about the practical power of any quantum computer as a combination of time factors. You've got coherence, you've got gate speed, you've got the time it takes to look at error correction codes, and in this case, we have a reset of those qubits that you use to measure parity. And so we go back to that race against the clock. You've got the coherence time, the time that a qubit stays coherent. Then you've got the gate speed. Now we've got the time it takes to look for errors. And add to that the time it takes to reset those qubits that are used for error correction. So again, IBM has not released any data on Loon's physical qubit quality. There was no discussion of coherence time, gate fidelity. Those numbers would ultimately decide how many errors occur per cycle. And it's also interesting to note that they talked about supremacy will be demonstrated next year. And so we talked about that arms race in quantum computing. We've got companies announcing things. IBM in this case is taking a very measured approach. They're saying, hey, we're focused on fabricating these chips at scale. They're focused on the nuts and bolts of error correction. They're speeding up some of the most important parts of it. But what IBM didn't do in this announcement, and I have respect for this, is they didn't go wide and announce that they've solved world hunger with a new quantum computing chip. I think what you're seeing here is an effort by IBM to communicate we're making real progress, we're focused on fabricating these things, and they also held back on publishing some of the statistics that you would ask about a new chip. A couple things might be possible here. Loon is a research prototype. It's not optimized for maximum coherence yet, so sharing the raw numbers might not be impressive compared to production qubits. IBM might prefer to refine it before publishing it. IBM also might have wanted to emphasize the system-level capability, the integration of features, the decoder speed, the focus on fab, rather than invite direct specification comparisons at the device level. They know competitors and the community will scrutinize any numbers, so IBM might choose to release those in a peer-reviewed context instead of a press release. And there's also a good chance that these metrics might be improving too quickly for them to announce something in November that could change dramatically in December or January. Innovation in this space is moving very quickly. Comparing this to Google's Willow, in the quantum race, Google has been tackling error correction as well. Error correction is the big thing, and they're using surface codes on its Willow processor. And that's what Google announced in 2023, that they scaled their logical qubits from 3x3 to 5x5 to 7x7. The logical error rate kept dropping. They reported logical qubit coherence times of around 290 microseconds. And I think the takeaway from the Loon announcement is they're telling you, we're making real good progress. We'll have more numbers for you next year. That's essentially what Loon was. But the real emphasis here is that multi-layered wiring means that they can create logical qubits or physical qubits that are not next to each other. So I would expect in the next year for IBM to publish a scientific paper that details Loon's design and performance. I'd also expect a demonstration of a logical qubit on Loon and comparison with Google and others. IBM also talked about Quantum System 2, and that's this next generation infrastructure that'll house multiple chips, and that's supposed to launch next year. One question is how Loon learnings will integrate into that multi-chip approach or distributed quantum computing. Watch for IBM potentially to combine multiple Nighthawk chips via couplers. IBM's roadmap mentioned Quantum Condor, and that was 1,121 qubits in 2026, and that's going to be likely achieved by linking chips, ensuring that the error correction works, and that expanded context would be another hurdle. So it's interesting, this Loon chip sounds significant, but we're not getting the full picture of it yet because it's new. But that's how the space works. Lots of press releases, lots of conferences, lots of numbers shared, but it's interesting to see these companies competing with each other on how they announce specific technologies. So that's my expanded coverage of this Loon news. I think it's interesting to watch, and the focus for Loon was on error correction, the time it takes to reset what's called ancilla qubits, the time it takes to process the error correction codes, and then fabrication. They're moving into the big leagues in terms of fabricating chips that incorporate quantum technology. And seeing how fast things moved between the 60s and the 70s and the 80s, I think it's still going to take time for this to scale. But remember, a $1 million computer in 1968 only had 4 kilobytes of RAM, 8 kilobytes of RAM. Think about the progress that was made in that area, and then fast forward 30 to 40 years in this area. And there's another news story we're going to cover today, and that is the Southern District of New York, the case NYTimes Company versus Microsoft Corporation et al. And this is really the NYTimes versus OpenAI. There was an order issued by a magistrate judge, Ona T. Wang, and I'll read it. Accordingly, OpenAI is now directed to preserve and segregate all output log data that would otherwise be deleted on a going-forward basis until further order of the court. In essence, the output log data that OpenAI has been destroying, whether such data might be deleted at a user's request or because of, quote, numerous privacy laws and regulations, that might require OpenAI to do so, so ordered. And this is interesting. This is an interesting thing to think about because there's this case that's going to be talking about copyright and fair use. And the main question is, training on copyrighted text and generating summaries may be fair use, but verbatim and near verbatim reproduction that substitutes for the original is likely not. And the other thing that this case is going to talk about is copyright management information. So if these models are being trained on the news, are they specifically removing the bylines and the titles when they reproduce content? And this is going to get interesting. It's going to talk about remedies. While this is all happening, you can also wonder whether or not Congress is thinking about establishing a new act, an act that would make it easier for these LLMs to operate without being sued every other day for copyright violations. And it's similar in some ways to what makes the internet work right now. There is something called Section 230, and that's in the Communications Decency Act, decades old now at this point. And that's a US federal law that protects internet platforms like Meta and X and everything from liability for content posted by their users. And think about that. If you go onto X, you can see some very awful things. Know that Section 230 is the reason why X isn't getting sued every day for everything a user says. Without Section 230, we actually wouldn't have much of the internet as we know it. It grants immunity for platforms if they have good faith efforts to remove objectionable material. They can't be sued for that. And that law was also intended to foster the growth of the nascent internet by giving online services broad protection against lawsuits for third-party content. So this interesting case has an order, and OpenAI is fighting back. As an OpenAI user, I'm very interested in this. If a court is ordering them to hand everything over, it raises questions about the persistence of all the data that we're sending to these services. And if you read the news, people are sending some fairly sensitive data to these LLMs. And if we can't guarantee that it's not going to be discoverable by a court of law, that changes our relationship to these services. So there's so many questions. There's so many things happening in this case. I think it's one to pay attention to because it's not just copyright here. It's also, what does the DMCA say about removing what's called CMI, copyright management information? That includes things like the author, the byline, the title, the copyright notice, the license terms, identifying numbers or links. If you remove that specifically when you're ingesting data, well, there's a law for that. It's called the Digital Millennium Copyright Act. So there's so many different interacting interests here. We're all affected by some of the privacy concerns that I think OpenAI has raised. I mean, let's just think practically. If this company is being ordered to maintain all the logs that they're generating from user conversations right now, what does that do for security? So if you're sending something to OpenAI, is it going to be preserved forever, even if you tell them you want it to be deleted?